Okay, so let's start talking about chapter 25, capacitance. And so before we get started, let's think about the flash of a camera. So let's see, what exactly is going on there? Essentially what happens is you get a buildup of, you have a stored amount of charge that you allow to come to equilibrium very fast. And so let's say maybe you have some kind of couple of wonky shapes. All right, we're going to start with like the arbitrary shapes and then we'll move on to specific cases, but we always like to try to start being very general. And so if you have these two shapes, you're going to have electric field lines going in between them. All right. Maybe you have some kind of stray ones coming around the back, coming out here. Right. However, and right, you have a pretty strong electric field in between these, right, which is the incentive for charge to flow, right? A potential difference creates an electric field, which is what tells a charge is experiencing a force, and that's what makes things move around. But these things are separated, so all this charge is kind of isolated. But if we were to take some kind of conductor and attach it to this, you can imagine you're going to get a bunch of positive charges running out of here and a bunch of negative charges running out of here, and they're just going to go to the other sides till you reach equilibrium. Right, which means there's no more electric field, and everything's going to come to be balanced. And this is going to happen very fastly, and that's going to release a lot of energy, and that's what makes the flash of a camera. Right, and so you might be thinking, why do we have to do all this? Why can't we just hook up a battery? Typically, when we want a potential difference, we use a battery. But the thing about batteries, they are good at maintaining a potential difference for a long time. But the reason they're not good for things like a camera flash is slow operation, right? And so if you have a battery in your, remote control for your TV or whatever, right, that's going to last for years before you have to change it out. So it's good at maintaining that delta V, but in doing so, it only lets a little bit of charge leave at a time. And so for something like a camera flash, we want all this to happen very fast. And so that's where capacitors come into play. And so let's try to figure out how much charge can be stored on our plates, right? Even if they're not plate shaped, we always call the two sides of a capacitor the plates. And this concept of how much charge that can be stored, that's called the capacitance. And if we're ever drawing this like in a circuit, right? Let's say you have a battery. Capacitor is always just two parallel plates. So it's plus minus for some delta V. Right, where for a battery, you always have one long, one short. For a capacitor, they're the same size. And so for what we're going to do is we're going to say the space inside our capacitor is empty. For now, at least. Okay. And so let's try to imagine what would happen if we have this setup. Right, so we have some potential difference. So maybe there's a large buildup of positive charge here. We got a bunch of negative charges down here. All of these positive charges on this plate together, like they want to get away from each other. And so we'll say, right, well, that erased more than I wanted, but we'll be okay. So slowly but surely, we're going to have charges traveling through this circuit. And when they get to here, they all start building up. Right, and I guess maybe let's not go to the fully charged plate yet. Let's say we have 2 charges on here. Right, so if we have 2 charges on here, they're going to make an electric field. I'm not going to do left and right. I'm just going to focus in the direction of the circuit. And so there's an electric field. We have a conductor down here. And so what's going to happen is any kind of free charges in that conductor are going to get pulled up onto this lower plate. Right? And so now we're going to get a couple charges here. Right? Just so that the electric field is now contained in the gap between these plates, but it doesn't go further. We can kind of get rid of that. Okay, and so we have that, and then we have maybe another charge traveling around. So we get a third one, we get a third one, and this is going to keep happening until the potential difference across our capacitor is equal to the potential difference of the battery, right? They're at the same voltage, the same potential. Right, and so the process just keeps happening until you get enough charge built up to resist that process. Right, once you have this entire kind of area here at that same positive potential, and then maybe this entire area here is all at the same negative potential, right, there's no more incentive for charge to flow. Everything kind of stops. And so that's how a capacitor charges up. Okay. And so we know, like, if the capacitance is how much charge can be held at a specific voltage, we end up, well, let's think about this. So as V increases, we expect Q to increase, right? If nothing changes about these plates, right? If we were to come along and add a bunch of extra charges here, we'd get some more here, right? So if delta V increases, then the amount of charge we can store will also increase. Okay. And then since capacitance is how much charge we can store, we also kind of expect as capacitance increases, the amount of charge would increase for a fixed voltage. And so we can say the capacitance is equal to the amount of charge on the plate for a specific voltage. Right, and that's going to be our definition of capacitance. You're probably going to see the equation written as Q equals CV more often. I kind of like the first way a bit more, but it's, neither here nor there. And so let's really briefly hop over to a FET simulation. Right? Yeah, no one saw that coming. Real plot twist there. Of a capacitor. And so let's go ahead and say we have some voltage, right? And so we can start at 0 volts, right? So there's nothing on the plates. As we increase this potential, we get more and more charge build up on the plates like we discussed. All right, as the charge builds up on the top plate, so does it on the bottom. And like when I went through this kind of argument of like the charge building up on the top is going to cause charge to build on the bottom, that's the way I like to think about it. You can also just think the negative plate is the source for negative charge. And so you get the positives going up, the negatives going down, and they just both go until the potential difference builds up. But it really doesn't matter. Right, and so like we said, right, these plates are unchanging, so we expect the capacitance to be fixed. But as we increase the potential, we get more and more charge, and that gives us more and more of an electric field. And so that kind of agrees with the equation C equals Q over V. Then let's see what happens when we separate these plates, right? If we move them further apart, we can see the electric field lines get less dense, right? They start extremely dense when close, and they get less dense. And so we expect that the closer the plates are, the stronger the capacitor is going to be. And then we can also look at area, right? The bigger the plates are, the more charge they can store, the bigger the electric field, the higher the capacitance. And so, right, without even looking at anything, we expect the capacitance to scale with area, and we expect it to be 1 over the distance between the plates. All right, and so that's just a good expectation to have, which we'll investigate that a bit more going forward. So let's go through and try to calculate capacitance. And so we have a little plan we're going to follow. Step 1 is going to be assume we have some charge Q on the plates. And so that'll typically look like a plus Q on one plate and negative Q on the other. Step 2, use Gauss's law to calculate the E field. Step 3, use E to find the potential difference between the plates. And then finally, step 4, if we have Q and we have V, we can go ahead and calculate C. All right, and again, we can do that because Q equals CV. Q equals CV. But actually, I think for most of our purposes, we are actually going to use C is equal to Q over V. Fun. We get to use the one I like. Okay. So let's start off with a parallel plate capacitor. All right, everyone's favorite type of capacitor. And so let's say we have 2 plates. And we get, all right, these plates conduct, so all the charge is on the surface. Oh, that's so many. Whatever, we'll be fine. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and I'm not going to draw field lines for each of these because that's going to get carried away, so we'll just do like every other. Goes from positive to negative. Okay, and we'll go ahead and say these are separated some distance D. So let's see, what was step 1 going to be? Assume we have some charge Q, so we'll go ahead and say we have plus Q, negative Q. 2 is we were going to calculate the E field due to Gauss's law, And so I'm going to draw the Gaussian surface to just be this. All right, we're just going to kind of look at one for now. And so let's see, what does Gauss's law tell us? We have epsilon naught, the integral of E dot dA is equal to Q enclosed. We can see Q enclosed is just our plus Q right here. And then we're going to go ahead and say this is going to turn into epsilon naught EA, right? And we can do this because the area vector is going to be parallel to the electric field vector, and the electric field is going to be a constant through this surface, so we can pull it out. And so we're going to have the equation Q is equal to epsilon naught EA. And we're going to star that one. And this was step 2. So step 3 is, well, we'll say, step 1, find E field. Use E to find V. Okay, and so we have delta V is equal to V final minus V initial. So we have the negative integral from initial to final E dot ds. And so let's see if we can be creative anywhere. So if we say our initial points here and our final points here, and we want to integrate this way, well, our ds is going in the opposite direction of the E field, right? We have a E field going down, ds going up. And so that dot product is going to give us a negative sign, which makes this whole integral positive now. And so we can say V is equal to the integral from negative to positive of E ds. And since we're inside our parallel plates, we know E is constant. And so we can go ahead and say our potential, we'll just write this again. EDS is equal to E. Well, so we can go ahead and say this is, some y equals 0. This point here is some y equals d, right? If the space is d, we can do that. And so we can just go ahead and integrate from 0 to d in ds. And so we get it's equal to E times d, right? And so we'll go ahead and write V equals ED, right? We've seen this equation before. And we'll call this equation double star. And so then if we have C is equal to Q over V, we have our Q as our start equation. So we can say star goes there, double star goes there. And so we have epsilon naught EA divided by V, which was ED. Looks like our E's cancel. And we get C is equal to epsilon naught A over D for a parallel plate capacitor. Which, if we kind of look at what we expected to scale like A over D, right? Scale like A, scale like 1 over D, same thing. And then we just ended up with a proportionality constant, epsilon naught. And so that's all fine and good. Okay. And so let's hop on over to a cylindrical capacitor. Alrighty. And so we're going to have, some inner cylinder, right? This is going to go in and out of the screen. And we'll say it has some charge on it. And then we're going to have our outer, I guess we'll give this a width because it's a cylindrical shell. Right, the outer cylinder, right? So this is going to be like a hollow pipe with a positively charged core. And then let's take that hollow pipe and go ahead and put some charge on it. And so we're going to say we have plus Q there, negative Q here. We can go ahead and draw our field lines. And again, these are all conductors, so we have all of the charge on the surface, right? So some of these negative charges should probably be more like on the surface, but it's okay. Okay, so that's a pretty good start. Then what we're going to want to do is figure out a Gaussian surface. Actually, we'll say the inner radius is A, outer one is B, and then we're going to go ahead and draw some Gaussian surface with a radius R. Okay, and so we'll calculate E via Gauss. And so we're going to go straight to Q, which is Q enclosed, is equal to epsilon naught EA, right? Because the area vector is going to be pointing parallel to the electric field lines. And at the surface, the electric field's a constant. At the surface of our Gaussian surface, it's going to be a constant. Important to note, the electric field is no longer a constant between the plates, right? So we can see as we're very close in, they're closer together, and then the further out we go, the further separated they are, as opposed to here, where the electric field is a constant throughout the plates. Which means when we get to step 2, we're going to have to actually evaluate the integral. Okay, and so let's see, what's the area going to be? We're imagining a cylinder that's going in and out of the screen with a radius R. So we have 2 pi R, and then just times whatever the length is going to be. All right, some arbitrary length going in and out of the screen. Okay, so if we want, then we can solve for E is going to be equal to Q over 2 pi epsilon naught L times R. And again, I'm just going to note that this is constant through Gaussian surface, but not between plates. Right, and so that was our step 2 to find the E field. We'll just no, I'm not going to write that. And so 3, we're going to use E to find V. And so let's go ahead and figure out what our path of integration is going to be. So I think, again, we're going to start on the negative plate, go to the positive. Well, we'll go ahead and do that so that we're aligned with the field vector. And so we're going to integrate this way. And so we get V is the integral from negative to positive E ds. And so E, we have this value here. I guess we need our minus sign. Do we? No, not yet. And so, let's see. The EDS is going to give us the negative sign. And so we have negative Q over 2 pi epsilon naught L times the integral from B to A, because L is a constant, right? That's some arbitrary thing. R is what can change. And so ds is going to be dr, right? Because we're integrating from here to here. So that's along the radial. And then over r. Right, and so the integral of dr over r, right? I mean, if we said dx over x, that's going to give us the natural log of x. Right, so the integral x to the negative 1 gets a little wonky because if you do to the n plus 1, you get an x to the 0, then you divide by 0, you're having a bad time. And so we have this identity, which I'm sure was proved in a few of your calc classes. Okay, and so then we get v is equal to negative q over 2 pi epsilon naught L times the natural log of A minus the natural log of B, which since we're subtracting natural logs, we can put them in the log and divide. And so we get negative q over 2 pi epsilon naught L times ln A over B. And if we want to get rid of the minus sign, we can just kind of flip A and B, right? Because if we moved these around, then that's the same as multiplying by negative 1, which gets rid of our minus sign. And so we get V is equal to Q over 2 pi epsilon naught L times the natural log B over A. And we'll call this equation double star. Let's see, what do we have up here? Oh, and then we're, actually, we don't even need to do that. We're going to make life so much easy. So much easy. That was a sentence. And so if we go to C is equal to Q over V, right, with this whole expression being V, we get Q divided by V, which is Q over 2 pi epsilon naught L times the natural log of B over A. And so we get the Q's cancel. And we get C is equal to, well, we're going to bring this up here. So 2 pi epsilon naught L over the natural log of B minus A. And then this is the capacitance for cylindrical capacitor. All right, and I wrote it this way because this chunk here, the L over ln B over A, that's all properties of our plates, you know, like the arbitrary length we picked that they're going to be, the radii of them, and then we have our constants out front. So I just think it looks nice written that way. Okay, and so let's hop into a spherical. Yeah, I'm going to keep the same picture, only now instead of picturing these as cylinders going in and out of the board, it's a cross-section of a spherical shell of some negative charge Q with a core of some charge positive Q. Okay, and so we can kind of start the exact same way. And so step 2 was to say Q is equal to epsilon naught EA. Now A is 4 pi r squared, right? Because our Gaussian surface here is now a spherical shell as opposed to a cylindrical shell. So where a cylinder had an area of 2 pi RL, a sphere has an area of 4 pi r squared. And so we get Q is epsilon naught E times 4 pi r squared, which we can go ahead and say E is equal to 1 over 4 pi epsilon naught Q over r squared. Right, which we've seen this before. This should be, a comforting equation we got to. And so now we're going to integrate. And so we have V is equal to, from minus to plus, E ds. We get the negative Q over 4 pi epsilon naught, integral B to A, dr over r squared, right? So we're integrating r to the negative 2. And so that gives us a negative 1 over r. All right, so that minus sign is going to go away. And we get Q over 4 pi epsilon naught, 1 over A minus 1 over B. All right, and so can we make this a little nicer? Yeah, I think we can. And so we're going to multiply this by B over B and multiply this by A over A. And we get V is equal to Q over 4 pi epsilon naught times B minus A over AB. Okay? And then we go ahead and do step 4. C is equal to Q over V. Right, and so again, we have a Q in V, so the Q's are going to cancel out. But let's go Q over 4 pi epsilon naught times B minus A times AB. Look at that, our Q's cancel. And we get, what do we get? 4 pi epsilon naught. Then we would expect like an AB over B minus A. Yeah. I was seeing if there was a way we could clean it up, but we did that in the last step, so that works. And so we have this expression for the spherical capacitor. Cool. And so then briefly, let's just look for an isolated sphere. And so if we imagine plus Q on our sphere, and then, all right, we still have A as our radius. And then if we think about what it means to be isolated, we could say that this distance B equals infinity, right? And then we can also say A is equal to R, the radius of our sphere. And so if we start with C is equal to 4 pi epsilon naught, okay, we are going to clean this up a little bit. So we can say AB over B minus A. If we divide everything by B, we get A over 1 minus A over B. Right, and why is this useful? Because we said B is going to be infinity, and so A over B goes to 0. And then we also said A is equal to R. And so we get the capacitance is 4 pi epsilon naught R for an isolated sphere. Right, and so we have kind of deviated from our definition of a capacitor, right? We said it was always going to be two things separated. But if you're creative enough about what you mean by two things separated, we can have some fun, right? Okay, so there's the isolated sphere. And now we're going to kind of pivot. Red's aggressive. I don't know why I was using red for so long. To capacitors in series and parallel. And so the goal for this is always going to be try to replace the system of capacitors with one equivalent capacitor. And so let's start with parallel. Let's say we have a battery. We'll call that B. Positive, negative. It's got some delta V. Okay, so now we have three capacitors. And we're going to call this one C1. That's a terrible looking one. This one C2, C3. We can say we have plus Q1, negative Q1, plus Q2, negative Q2, plus Q3, negative Q3. And let's discuss the potential differences real quick. Well, this whole region is all connected. And then this whole region is connected. And they're connected by conductors, right, which we discussed there's no potential difference within a conductor at equilibrium. And so we can go ahead and say these all are equipotential at the top and then a lower equipotential at the bottom. And so what we get is if this has some potential V, so does this, and so does this, and so does this. And so we get for capacitors in parallel, they all share potential differences. All right, and that's just a rule that we're going to have. Okay. So that's fun, that's great. And so our goal for this, as we said, is to rewrite this as some C equivalent with some plus Q, some negative Q, and where we have V. All right, and so, right, we don't expect V to be any different from our initial V, right? It's the same battery, everything's good there. And so we can say Q is the total charge, and so we can say that's equal to Q1 plus Q2 plus Q3, it's a 1. Okay. And we can say Q1 is equal to C1V. Q2 is equal to C2V. That's driving me crazy. And Q3 is equal to C3V. All right, and so all we did is we took our equation, Q is equal to CV, and we just plugged in for each capacitor. Right, using all the values that we had here. Okay. And so then we can take these Q1, Q2, Q3s and plug them into here. And we get Q is equal to C1V plus C2V plus C3V. So we're going to factor out the V, right? Each one's multiplied by V, so we can do that. Okay. And so now we have the total charge and the potential, and we know Q is equal to CV. And so we can go ahead and say this is the equivalent capacitance. All right, so if we say CEQ is equal to Q over V, right, we can plug in the C1 plus C2 plus C3 times V, divide that by V, and we get it's just equal to C1 plus C2 plus C3. Right, or we could rewrite that as CEQ, and we're going to say J equals 1. Right, usually we have I as our index, but I is going to be current, so you're going to use a J. And CJ. And this is for N capacitors in parallel. Cool. And so what are we going to look at next? Probably series. And so we'll start with something similar. We have a B, positive, negative. It's a bit much. Okay. And so we're going to call that C1, C2, C3. We're going to say we have some total potential V. And so now if these kept the same V, right, if this was also V, that's also V, that's also V, then we would have a potential drop of 3V, but only be providing 1V. So that's not right. We can't do that, right? Whatever drop we have has to be equal to whatever we give it. Okay, so we'll go ahead and call these V1, V2, V3 with the expectation that V is V1 plus V2 plus V3. Okay, and so now let's kind of think about what would happen if we had some charge plus Q on this plate. As discussed before, right, if you get positive charge on this plate, it's going to attract negative charge on this plate, and it'll keep doing so until you have the same magnitude of charge. Okay, well, if you've just pulled all the charge from, below in the circuit, right, this wire, this plate, however you want to think about it, you just took a bunch of negative charge out, and so that's going to leave you with plus Q on this plate, which is then going to cause negative Q to get pulled up, which will leave us with plus Q, which will pull up a negative Q. And so all of these plates have the same magnitude of charge, whether it be plus or minus Q. I guess then we should also keep in mind what we're trying to do. A little something like that. Plus Q, negative Q. Right. And so just an equivalent circuit where we're going to kind of sum up the individual potentials to get to the total potential. Okay. And so we started with this, which is pretty good. But we can say V1 is equal to Q over C1, V2 is Q over C2, V3 is Q over C3, And so then if we want V is equal to V1 plus V2 plus V3, we can say that's equal to Q times 1 over C1 plus 1 over C2 plus 1 over C3. Okay. And then if we know the equivalent capacitance is going to be Q over V, all right, which we got from this circuit here, we can say that's Q divided by Q times 1 over C1, 1 over C2, 1 over C3. The Q's cancel. And so we get the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3. Okay. Which I think is typically going to be rewritten as 1 over CEQ is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So we can do the sum J equals 1 over CJ. That's the way it's typically written. I kind of like to write it like this. Just because we're not typically looking for 1 over capacitance, we usually want to find the capacitance. Right? And again, 1 over x plus 1 over y to the negative 1 is not equal to x plus y. And you can plug in some numbers if you want. Yeah, what the hell? So we'll do 1/2 plus 1/4 to the negative 1. So we can take this 1/2, make that 2/4, so we get 3/4. So that's equal to 4/3, which if we just did x plus y, that would be 6, right? 2 plus 4 is 6, right? And so not equal. Just so we're all convinced of our, strange little algebras we get sometimes. Okay, and then let's just wrap up with the energy stored in an electric field. Right, the textbook goes through some integrations to get to these. I don't think it's exceptionally helpful to do that at this level. So we're just going to go straight to the equations. So we have Q squared over 2C, which if we have Q is equal to CV, we can also rewrite this as U is equal to 1/2 C times V squared. All right, and so these are both the same expression. And then sometimes we want the energy density, which is a lowercase u, and that's going to be equal to the total potential energy over the volume, which for, let's say, parallel plates, we could have U over AD, right? The area times the separation gives you the volume in between the plates. Which we can plug in for U is 1/2 CV squared, and we get CV squared over 2AD. We know C is equal to epsilon naught A over D. So we can say epsilon naught over 2 times V over D squared. But V over D is equal to the electric field, the magnitude of it. And so we can get to the result lowercase u is 1/2 epsilon naught E squared. Cool. So we didn't get to dielectrics, but we'll talk about that a bit in lab, and I think that'll be okay. So I think we can probably wrap it up here. All right, cool.